Welcome to Homework Lib.
Hi. So for this question, let's begin by doing a quick review of what is going to happen when we have the concentration of HA and concentration of A minus. Actually, I'm just going to flip it up just for this to look more close to what happens in the Henderson-Hasselbalch equation. And recall that this is the amount of mole of A minus divided by a total volume divided by the amount of mole of HA divided by the total volume. So the total volumes are going to cancel out, and we can represent that coefficient of concentrations as the coefficient of the amount of mole that we have in our solution, because the total volume in solution is going to be exactly the same. Taking that into account, we are asked what is going to be the pH of a solution where we started with 9 millimole of HA, and then we added 1 millimole of a strong base. So if we look at our ice table for this reaction, the reaction that is going to happen is that we're going to generate A minus plus water. The other information that we're given is that the Ka for this is 5.61 times 10 to the minus 6, and this corresponds to the pKa equal to minus logarithm of that number. So this is a pKa of 5.25. Perfect. So now, if we go ahead with our ice table, what we are going to see is we start with 9 millimole and we added 1 millimole of OH minus. That means that the limiting reagent is going to be OH minus. So the amount of change is 1 millimole minus 1 millimole, and 1 millimole of A minus it's going to be produced. At the equilibrium, we're going to end up with 8 millimole, something close to zero, and 1 millimole. As you can see in this reaction, we have present in solution an acid and its conjugate base. That means that we have a buffer. And how do I get the pH for a buffer? I use the Henderson-Hasselbalch equation. pH is equal to pKa plus logarithm of the concentration of A minus divided by concentration of HA. But over here we already said that we can substitute these values. So in our case, the value for pKa is 5.25, and the values for concentration, I actually can keep them in millimole because both of them have the same units and they are going to cancel out. If you want, you can write it down as 1 times 10 to the minus 3 mole divided by 8 times 10 to the minus 3 mole. Just notice that the times 10 to the minus 3 is going to cancel out, so this is going to be logarithm of 1/8. So the result for this is going to be a pH of 4.35. Actually, I'm going to round it up to three significant digits. And what can we say about this? Well, we can say that the pH is lower than the pKa. Let's see if that makes sense. That would be true if we have more of the acid than what we have of the conjugate base. In this case, indeed, we have more of the acid than the conjugate base. So we would expect the pH to be lower than the pKa. Next up, what we want to know is what is the pH of the solution at the equivalence point. I'm going to skip a little bit of doing the ice table again, but what I want you to notice is that at the equivalence point, I have added the same amount of OH minus that I have added of OH minus. So that means that at the equilibrium, assuming that the reaction is complete, I'm going to have 9 millimole of A minus. You can verify the ice table again. Here it would be -9, -9, something close to zero, something close to zero. and 0 plus 9. And that would be all, right? So now, in order to know the pH at this point, we need to look at the inverse reaction of A minus plus water. That is going to generate HA plus OH minus. And to simplify things a little bit for us, now we need to know the concentration of A minus. We are told that the volume at the equivalence point is 44 milliliters. So we are going to have 9 times 10 to the minus 3 mole divided by 44 times 10 to the minus 3 liters. So the concentration of A minus that we're going to get initially at the equivalence point is 0.2045 periodic. Just for simplification, I'm going to call this C0, or even better, let's call it CE because it's the concentration at the equivalence. We are going to have initially concentration at the equivalence point, 0, 0, and 0. The amount of change, let's say that an X portion is going to react. Now this ice table, it is in molarity. Water doesn't matter, it doesn't enter into the equilibrium equations. We're going to have plus X and plus X. So at equilibrium, we have the concentration at equilibrium minus X, X, and X. Now, this reaction corresponds to Kb, not to Ka. So the Kb is equal to concentration of HA times concentration of OH minus divided by concentration that we found at equilibrium minus X. Sorry, at the equivalence, not at equilibrium, which is the concentration of A minus, of course, right? So this becomes X squared divided by concentration at the equivalence minus X. We know that Kb is going to be quite small. How do we know this? Because Kb is nothing but Kw divided by Ka. And Kw is 10 to the minus 14. The value for Ka is 5.61 times 10 to the minus 6. So the result that we're going to get for Kb is going to be 1.78 times 10 to the minus 9. So indeed, a very, very small value. This implies that X is going to be small. So we can make the approximation that my concentration at the equivalence, that is 0.2045, it is going to be much larger than X. Under that approximation, this number becomes concentration at the equivalence, right? So X squared divided by this concentration. Thus, the final result for X is going to be a square root of Kb times my concentration at the equivalence. The value for Kb is 1.78 times 10 to the minus 9 multiplied by my concentration at the equivalence that we found to be 0.2045, giving us a value of 1.91 times 10 to the minus 5. Now, let's review what is this X. This X is nothing but the concentration of OH minus that we're going to get at the equivalence point. So, the POH, that is minus the logarithm of concentration of OH minus, will be 4.72. And the pH, that is 14 minus POH, will be 9.28. And that will be all for this problem. This is the final answer for the second part. Thank you very much. Have a good one.